if you have interest in air compressors, gas compressors, such as a natural gas pipeline transmission compressor, the compressor section of an automotive turbocharger, or the compressor of a refrigeration system, this video is going to be important for you because we introduced the idea of compressor efficiency. So we're going to cover the general statement of compressor efficiency. In particular, this applies to compressors where the casing is fully insulated. So in our model, we're going to consider that the compressors we look at are fully insulated, and any cooling of the gas is done outside of the compressor itself. So there may be an after cooler or something like that. But for our compressor study, we're going to consider that our compressors are fully insulated. So let's refresh our memory. What is a compressor in the first place? Well, here's a great shot of an industrial, this would be a single stage centrifugal air compressor, industrial size. And over here on the right, this is going to be a multi-stage centrifugal compressor where you see, at least in the sketch, or at least in the picture, you see 1, 2, 3, 4, and then it looks like in the last 5 sections of compressing a gas, probably air. And the other thing to do, this is such a classic image because you can see, since the direction of flow is from left to right, you can see how the specific volume, or the volume of the gas, is decreasing and decreasing and decreasing as the pressure goes up. So we've covered compressors in Chapter 4, and so I might remind you that in the Chapter Key Points playlist, you can click on Chapter 4, Part 8 to get a little more background on how to deal and make calculations associated with compressors. Let's remind ourselves about the difference between W dot out and little w out for an open system, and particularly a compressor. Now, typically in our studies and in our experience, compressors are operating typically at steady state, steady flow conditions with one inlet and one outlet. So you can see on my sketch, I've just got a single m dot. The m dot 2 is going to exactly equal m dot 1. We're going to consider that we're under steady state, steady flow conditions to really simplify our model. So you notice here I did not show Q dot in to a compressor surface. That's because in our dealings in this compressor efficiency definition, we're going to consider that our compressor is fully insulated. Let's see, what else did I show in my sketch? W dot compressor is less than 0. So although I'm showing a block arrow going out, we all realize using common sense that it takes power to drive a compressor. And so I don't show my W dots with an arrow going in. I simply show W dot out of the compressor is less than 0. And then reminder to get caught up with your textbook and other traditionally accepted analysis methods. Little w out is W dot out, the power, divided by the mass flow rate. So W dot out over M dot out equals little w. And okay, and I see in my yellow text box, I'm reminding everybody that, so for a compressor, little w is a negative number. Let's consider a compressor in my sketch. And let's say that this compressor in the sketch is reversible and adiabatic. Now, what does that mean? Oh, I forgot to mention, for compressor, a piece of equipment called a compressor, we're nearly always dealing with ideal gases. We're compressing ideal gases, or gases in general. We don't encounter steam compressors. So the nice thing here is we're going to be able to draw a TS diagram that doesn't show a vapor dome, because we're only going to be interested in analyzing compressors that are using gases, or in particular ideal gases, as the working fluid. So let's consider a reversible and adiabatic compressor. What does that mean? It means within the compressor itself, there's no frictional losses between the shaft and the seals. You can see how conceivably for this sketch, there could be some friction if there's rubbing. Well, there's none of that. There's no unrestrained expansion. In other words, there's no pressure gain losses. That would be unrestrained expansion throughout the process. And so our TS diagram for the reversible adiabatic process, compressor process goes from a low pressure P1 up to a higher pressure P2. And I'm going to call my process 2I, and that's going to represent state 2 for the isentropic process, 2I. Now, that's not exactly consistent with the book. The book will call it 2S, but you get the idea. This is also a solid line because for our reversible adiabatic process, it's considered quasi-equilibrium process. At all points, the gas is in equilibrium from 1 to 2, and so we can look at the area under the curve to visualize the heat transfer on the TS diagram, and I see, well, there's zero. There's no area under the curve process 1 to 2. That's good because it's an isentropic, it's reversible and adiabatic. That means no heat transfer, so we're consistent here. So you've got a good handle on what the isentropic compressor would look like, and you've got probably enough skill now to be able to determine how much, if you were given the mass flow rate m dot, you could probably calculate the power required to drive the reversible adiabatic compressor. I hope you could do that. Okay, so, but let's move along. Let's say that our real compressor, our real honest-to-goodness compressor, has some type of irreversibilities inside it. And so maybe that frictional rubbing on this image, maybe some friction between the rotors and these seals could be an example of a frictional process that would make the compressor have some irreversibilities in it, right? So what would the process 1 to 2 actual look like for an insulated compressor, fully insulated compressor that's got some irreversibilities? I think you could satisfy yourself going back to the definition of entropy production rate for open systems and other reasonings. You can satisfy yourself that for this insulated adiabatic process, S2 is going to be bigger than S1. Little s2 is bigger than little s1. And so that's why I've labeled my end state of the irreversible adiabatic compressor to be 2A for 2 actual. And I'm showing it as a dashed line because the reason that we engineers show it as a dashed line is to indicate that you can't look at the area under the curve and visualize the heat transfer. And this is a good example, right? We're going to say that the casing of our compressor is fully insulated. Wow. And so it's a clear definition or clear example that we couldn't look at the area under this dashed line to figure out the heat transfer because we're saying we're fully insulated. Thus, the dashed line can't get the area under the curve. So that's an important point to make. And also, I'm not sure if I've made this point in this video in a subsequent slide, but notice that the book calls this point here 2S, 2S. I call it 2I because it's easier for me to remember 2 isentropic with the I. Now, the textbook also calls this point just 2. And I found that harder to visualize and understand. It's so much easier for me to label my state 2A for 2 actual so that I've got something that's very similar, but reminds me in my mind that I've got state 2 actual and 2 isentropic, both of which are going to that upper pressure P2. Okay, let's do some common sense reading. So have I convinced you that little w and w dot, both of those are going to be negative numbers for a compressor? Hope I've got that. Okay. Which process will require more power or less power? Process 1 to 2I or 1 to 2 actual to operate this real honest-to-goodness compressor. Here's the electric motor. What does your common sense say will take more power to run? An isentropic compressor or an actual compressor? What do you think? Well, My common sense tells me that it would take less power to drive an isentropic compressor than it would to drive an actual compressor. And let's look at this time. So which which dot would you think would be 2I and which dot would be 2A on this sort of linear line where we have measures of power? You see, I've labeled this line, here's a 0 where no power is required. To the right of 0, do you see that W dot out would be kind of like a turbine, wouldn't it? Power is produced. W dot out is greater than 0. To the left of 0, that's where power is required. So W dots are negative numbers. So which would you figure would be process 1 to 2I and which would be 1 to 2A? So I think the answer is that this would represent 1 to 2I, and this would represent 1 to 2A actual, because little w or W dot is more negative. There we go. So there's the answer. Process 1 to 2I is here, and process 1 to 2A is here. That sort of fits with common sense. Now let's apply a little more common sense. What we want to do is we want to define compressor efficiency. Compressor efficiency. So instead of just going to the textbook and looking for a formula and say, okay, oh, here's my formula. I will write that down on my formula sheet. What would you expect an efficiency value for a compressor to be? Would you expect it to be less than 1, exactly equal to 1, or greater than 1? Well, I think your common sense tells you that some measure of efficiency is going to be some number less than 100%. It's going to be less than 1. So that your common sense is good here. Okay, so I'm going to suggest if you use your common sense, you can write down the definition of isentropic compressor efficiency without having to go to the textbook. So the definition of eta compressor, this is Greek letter eta, by the way. In the turbine video, I went on and on talking about how embarrassing it would be if you called this N of the compressor. This is Greek letter eta. And so you always want to express the compressor efficiency, similar to turbine efficiency, as well as thermal efficiency, as eta, Greek letter eta. Compressor efficiency is defined as, well, the less negative value. It's going to be a negative number, but W isentropic divided by W actual, because you see, okay, that's a negative number, but this is going to be even more negative. So the negatives will cancel. So W isentropic over W actual is going to be a ratio. It's going to be a positive number, but it's going to be less than 100% or less than 1.0. In common practice, typically we engineers have the ability to determine W isentropic. We can figure out W dot over M dot for an isentropic compressor from usually given information. And very commonly, we are given the compressor efficiency and we have to find W actual, W dot over M dot actual, or A, okay? And so I just rewrote this definition of compressor efficiency here because this is typically what I'm doing when I'm making my analysis of compressors. Okay, so here is a repeat of this would be a TS diagram for an ideal gas. No vapor dome here, it's an ideal gas. And so just to repeat, what's the purpose of a compressor? To increase the pressure from 1 to 2. So we've got a low pressure starting at state 1, 2 candidate processes, the isentropic process that I have mislabeled. Yikes, I'm going to have to look at this. This should be 2I over here, right? Wow. And 2A should be over there. Wow. So that's a big visual blunder that I'm going to have to go back and correct my slide. Okay, 2 isentropic, 2 actual. Sorry about that oversight. But you're smart enough to pick up on that. You can make that correction. Now, the devil's in the details for these compressor calculations. And instead of dragging you through some example problems in this video, now that we've got a definition of compressor efficiency and you use some common sense to be able to say, I don't really need the textbook formula given that. I can figure out compressor efficiency out of my head. Compressor efficiency is going to be the isentropic work, the lower negative value, divided by the actual work, the more negative value. So I can figure that out. I don't need a formula or a formula sheet to get that. The devil is in the details. And so when you're working with an ideal gas, you have to make some decisions on, do I have an ideal gas with constant specific heat? Do I have an ideal gas with variable specific heat? How do I determine various properties for an isentropic process and for an actual process? And so let me try to chase you to my example problems, open systems playlist. And if you scroll down and you can find compressor calcs, and you'll be able to find some example problems that might help you with your understanding of dealing with compressor efficiency. Sorry about that TS diagram improperly labeled. That was a big oversight blunder. So what did we do in this video? We reviewed the objective of a compressor is to increase the pressure of a fluid and get the fluid moving from one place to another, right? We defined isentropic compressor efficiency. My claim is you can figure out the definition of compressor efficiency simply by using Common Sense 101 instead of depending on the formula. I certainly will say that the devil is in the details for making engineering analysis of compressors. So in the problem-solving process, and you're going to be analyzing a lot of compressors subsequently in this class. A compressor is an extraordinarily important part of a gas turbine engine. Air compressors, of course, stand alone by themselves. You'll be studying the compressors of a refrigeration cycle, vapor pressure refrigeration cycle, and air conditioning cycles full of compressors. And so the devil's in the details for making those computations, and I try to chase you to my video to give some examples. Okay, so I hope that helps. And now what have we done? I hope you've seen the turbine efficiency video, definite turbine efficiency. That's going to be, let's see, that's going to be actual work divided by isentropic work. So less than 100%. Compressor efficiency, that's going to be isentropic work divided by actual work. So you put the more negative number in the denominator, the less negative number in the numerator. So don't forget, if you get confused, if you start to panic, don't go to that formula sheet. Go to Common Sense 101 and your head to be able to figure out what the definition of these various efficiencies really is.